let's begin by, who our two speakers are today. So we have Danny Bluestein and Leonie Huddy. As I've said, they've been asked to prepare a somewhat shorter and more general presentation, and I think we will all get quite a bit out of it. So Dr. Danny Bluestein will go first. He's a SUNY Distinguished Professor in Biomedical Engineering. He's been at Stony Brook since 1996. Now I'm gonna save a very thoughtful and comprehensive introduction of him for his chair, Yishen Chin, but what I'd like to do is just say a few words about Yishen. He's a SUNY Distinguished Professor and Chair of Biomedical Engineering. He's the Director of the Orthopedic Bioengineering Research Laboratory and co-director of the Institute for Engineering-Driven Medicine. He's been a part of our faculty since 1998, and his research is based on physical mechanisms involved in the control of tissue growth, healing, and homeostasis. I will also say he has, in some ways, one of the hardest chair jobs at the whole university because he sits across two different schools and colleges. And I don't know if I even believe this is true, but apparently those two deans live on either side of your house. Is that really true? So I don't know. I mean, maybe that's just like the new rule. So if you're in an interdisciplinary, the deans live on both sides. So who knows with that. But what I appreciate about Yishen is he is so thoughtful as a chair. He is really, really focused on faculty development. Biomedical engineering has some of our most prolific, some of our strongest personalities, and faculty that really are doing amazing things, and it is really hard to be a great chair and to try to figure out the ways to support faculty who are pushing the boundaries of their field, of teaching. It is really a special department, and I think that specialness, a lot of that goes to Yishen and who he is as a leader, what he embodies, the message he sends as a great researcher himself, someone who cares deeply about teaching. He is truly what we hope for when we think about a leader who is also someone who leads from within. So with that, I will bring him up and we will start our series today.
Thank you, Carl. And also, I would like to thank Carl and Monica and the whole team try to highlight our own faculty at Stony Brook and for their research, their teaching, their achievements in the nation and the world. And this brings to my great pleasure to introduce Dr. Danny Bluestein. And he's currently SUNY Distinguished Professor and in the Biomedical Engineering and also in the Engineering and Applied Sciences College. And also, as Carl mentioned, that our department report to deans, and then it is not easy job. But anyway, we got through. And so Danny is, he got his doctoral degree from Biomedical Engineering at Tel Aviv University in Israel in 1992. After a short postdoc training and also visiting professor at the Department for Biomedical Engineering at the University of Miami for a short period. And Stony Brook is very fortunate to recruit him to be a newly formed biomedical engineering program as the first faculty member and into our program in late 1990s. And then become one of the 4 founding faculty member in the BME department we formed in 2000. Luckily, 4 founding member, we still have 3 of them still within the department. Our distinguished chair, Colin Rubin, and also founding chair for the department, still here, and Danny's here, and myself. And welcome, excellent too. So as a department, I think we have a lot of students here, and I'd like to say something by the career path, and using Danny as a great example. And Danny joined us and then formed our department in 2000, and then he became the assistant professor, moved to the associate professor tenured, and then full professor, now become the SUNY Distinguished Professor. And his career path almost all in Stony Brook. And grow up, become like a world leader in biomedical engineering, and particularly in vascular skeletal biomechanics, regeneration, and also the translational medicine. And I just want to give one example for his research. He developed kind of a prosthetic polymer heart valve. As we know, heart valve is one of the disease which is impact the human body and quantified as the top 3 cause of death. So he and his team really developed a valve called a TAV valve, which can replace the old kind of a heart valve transplant, physical surgical transplant, into the catheterizing and insertion for those artificial valves. Those save tremendous millions of patients' life, and his group really lead on this project. This is one of the examples. He also have a lot of research related to how to grow tissue in the lab and then eventually implant into the human body. And he has a vision in the cardiovascular biomechanics research and also higher education in a very elevated, enthusiastic, very energetic way, and serve as a research for the university. And he also have a research in the platelets function with cardiovascular disease and microcirculation, artificial machine learning, deep learning, and also for engineered heart valve. And he also developed numerous kind of a computational model to do the fluid flow within the whole body and try to quantify what kind of a disease formulation and how to control disease. And he designed those combined experimental and analytical approach all together to tackle very complicated and cardiovascular fluid behave within the vessel and the heart. And he also contribute deeply to our education. He is one of the faculty members develop undergraduate course and a graduate course for our undergraduate program. And I have to say something for the program. We developed a graduate program and also undergraduate program in 1998 and 1999 and a former department in 2000. Now we, from scratch, we have almost like 300 undergraduate students in biomedical engineering and 100 students in biomedical engineering graduate program. All combined together, we have almost like half of a student's body is a female and contribute tremendously to our education and research in our program. And overall, I think Danny is contribute to both research and education. He's now the fellow of the American Institute for Medical Engineering, and also the fellow for Biomedical Engineering Society. And he received numerous awards. One of the highest award is the ASME Savio Wu Translational Biomechanics Medal in 2021. So this is one of the highest medal from the ASME, the society. And overall, I think he contribute outstanding scientific contribution to the biomedical engineering, and also contribute as the outstanding educator and a mentor to our students, and provide a great service to the university. And the last word I want to add is that he is also very, very talented musician, and he can play great the guitar. And I hope he can play today, but there's maybe no time. Without further ado, and I think Professor Danny Bluestein.
Thank you so much for this generous introduction and also the opportunity to present to the community and the university community at large. So what I'm going to try to, let's say, dampen you today is a bit of innovative medical technology that is now being implemented for a couple of decades. And basically, innovative prosthetic heart valves for minimally invasive treatment of cardiovascular diseases. And I'm going to describe to you what motivates us in this type of research. So first of all, what disease are we dealing with? Specifically, I'll concentrate, and this is just one aspect of our research, on calcific aortic valve disease. And this is a progressive disease that causes the narrowing of the aortic valve opening. So what you see here is a healthy aortic valve. The aortic valve is located between our heart main pumping chamber called the left ventricle and the aorta, the major blood vessel. And its function is to keep the blood flow unidirectional when the blood is ejected by the pumping ventricle to the rest of the body, and then close immediately to prevent it from flowing back into the pumping chamber. Now, in calcific aortic valve disease, what we see is this formation of large calcifications. And when the disease is mild, it already impairs the leaflet's motion and opening and closing. Then you can see here a moderate stage of the disease, and then the severe case, which you can see a totally dysfunctional valve that hardly opens and closes. Now, what does it do? When the valve opening is being narrowed, if you think about your Monday experience of, let's say, watering your backyard with a hose, if you want to reach further, you squeeze the end of the hose, and then you see a jet of water coming out. So the same thing happens in our bodies, which could be pretty problematic because this higher velocity also translates to elevated stresses on blood cellular contents and affecting directly those that increase the risk of blood clotting, called the platelets, by the way. It also increases the pressure that the heart needs to produce to overcome this additional resistance because it doesn't fully open and close. And so the heart has to work much harder. And this may lead to heart failure. And in a severe case of aortic stenosis, it may result in a heart attack. And in that, I would like to draw your attention to sub-cohort small of patients that are born with a bicuspid valve configuration, means only two leaflets. It's a congenital defect. And for these patients, the disease, if it happens, occurs at a much younger age and progresses much faster because inherently they have a limited orifice because of this special configuration. Now, don't be overwhelmed by this very biological-based slide that you see here, but what you see here is a zoom into the surface of just the aortic valve leaflet. And the process that starts this buildup of calcifications is similar to atherosclerosis disease in coronary arteries, those that constrict the blood flow in coronary arteries. And basically, you have intrusion of the bad cholesterol, the LDL, but also because of the accelerated blood flow, there's a certain process because of the additional stresses that is called mechanotransduction that does something very surprising. It triggers a certain cell called fibroblasts to turn into osteoblasts. Osteoblasts are bone-forming cells. This is very surprising. Bone formation inside our heart valves. And the problem with that is that this accelerated form of bone formation doesn't necessarily form bone, which would have been bad anyways, but they actually start calcifying because this is how our bone becomes rigid. And those are exactly those large calcifications that we then see. Now, naturally, this is more like an elderly population type of the disease. And at the severe stages of the disease, because of the heart failure, up to 20% of the patients are inoperable. So there was for years an unmet clinical need because you cannot do open heart surgery where you open the chest, expose the heart, stop it, and resect the aorta, remove the diseased valve and implant instead the prosthetic valve. Nowadays, mostly bioprosthetic valves. So there was an unmet need to invent some technology. How do we treat those patients that cannot tolerate cardiothoracic surgery? So the transcatheter aortic valve replacement is based on some idea of stenting arteries. So I'll describe to you the procedure in a moment. Now, it started to treat these high-risk inoperable patients, but it quickly expanded to younger and low-risk patients because it's a minimally invasive operation, and in that also recuperation is much faster and whatnot. And this is actually a problem. Here you see such a device, and here you see one of the most famous patients, Mick Jagger from the Rolling Stones, who underwent transcatheter aortic valve replacement around 6-7 years ago. So jumping jack flash is jumping with this valve. It's doing pretty well, because I'm going to describe what may go wrong with this type of procedures. So let me just show you an animation which shows how it's done. So the valve is crimped into a stent, it's inserted through an artery near the groin femoral artery, and then it's navigated right there and deployed over the diseased valve without resecting it and removing it, pushing the calcifications apart, and opening the orifice. Now, initially, this was a huge success. And basically, the idea was to adopt existing bioprosthetic valves. Now, bioprosthetic valves are made of tissues harvested from animals. For example, bovine pericardial tissue. This is a fixed tissue. It's not a living tissue. So they crimp it into the stent by designing such a device, and then deploy it. Now, one of the first risks that occurred is actually how good is the anchoring of the device once it's deployed. There's a certain risk of migration. So that's one thing. Another thing, during the deployment, does it offer a complete seal around the prosthesis? If you recall these large calcifications, it's not unclear whether it will achieve this complete seal. And the problem with that is that then you have leakage flow that is called paravalvular leakage, and this is very thrombogenic. It may start a thrombosis process, which could actually thrombose the valve. This is an explanted failing TAVR device that basically became dysfunctional. And also it increases the risk of stroke. And yet another potential risk is the way those devices are deployed and designed is such that they push against a very important electrophysiological node of the heart, which is called the atrioventricular node. And if the stress on it may be too hard, it may induce heart arrhythmias. And then you may need to implant a permanent pacemaker in the patient. So what started as a minimally invasive procedure now became much more complex procedure. Additionally, because this is a fixed tissue, when you crimp it into the stent, and the stent is 5-6 millimeters at the most, you may damage the tissue itself, and this may lead to structural valve degeneration. So this will limit or impair the durability of the device if this is the case. And recall that I told you that it rapidly expands to younger and lower risk patients because it's convenient to have this easier procedure. So we set out to study these possible risks and problems using the concept of digital twin, which is basically a virtual representation of a patient. So we start with obtaining CT scans of pre-procedure patients who are candidate for TAVR, and then we fully reconstruct the full anatomy and geometry, patient-specific in that, without getting into all the details, but we end up with a very detailed and pretty precise anatomy of the disease with the calcifications and characterization of all the material properties of the soft tissue. We then also simulate the whole procedure. Some of these devices are expanded by inflation of a balloon like you see here. And we also simulate the crimping of the valve into the stent. So how good does this correspond to what is observed in patients? So you see that the numerical simulation can predict very well exactly what we see in the patient. That's the main idea of a digital twin. Now, this enables us, for example, to study the risk of migration by looking at different locations where we could deploy the valve to get the best anchoring secured. Then we actually could replicate an accident that happened right here in a university hospital operating room where a TAVR device was deployed too proximally, which means that it extended a bit too much towards the left ventricle. And once it was deployed, the device popped back into the ventricle. the patient was rescued, so the patient survived. But we wanted to study and to see if the implantation was done differently, if it could be avoided. So what you see here, follow the green curve here. This is the accident, because what's plotted here is the contact area of the device. This is the case where it totally lost the contact area. This is when the popping back into the ventricle happened. And if it was deployed in 2 different other locations very close by, this would have been avoided. The contact area won't have been lost. Now, in recent years, we started research collaboration with the Simulia Living Heart Human Model, the Living Heart Project. This is a subdivision of the Life Sciences Division of Dassault, the French airplane manufacturer, who does also this. And they developed a very unique model that is electro-biomechanical model of the pumping heart. So we, of course, adopted it because this would facilitate to study the interaction of such prosthesis under real pumping condition of the heart. And this can be used for improved pre-procedural planning. So here you're going to see deployment in different locations of the devices, and in a moment you're going to see the heart start pumping. This is virtual. It's the digital twin of it. So you can see right here. And then we can study, for example, the contact area of the anchoring and contact force, etc. But actually, our main motivation, and you're going to see in this case, was what happens if it's pushing too much against this AV node, this electrophysiological node, and create the heart arrhythmias, also known as cardiac conduction abnormalities. And in that, we started several years ago collaboration with Georgia Bossi from University College of London, and she studied a large cohort of TAVR, transcatheter aortic valve replacement patients, and we actually found out that all the patients that required pacemaker implantation following the procedure had on average twice something that is called hoop stress around the prosthesis as compared to all these patients who didn't require that. So that was a clear kind of almost diagnostic type of work. Now, we now do much more refined simulations using the pumping heart model. As you can see right here, so this enables us to study the behavior under dynamic pumping conditions. It also enables to look at this risk of the leakage. Here you can see leakage channels formed because of the incomplete sealing once the device is deployed. And the question, and this again goes for pre-procedural planning, that is there a location that will mitigate it or at least minimize this? And we indeed found. Now, all this is studied in patient-specific anatomies, so it could be patient-tailored in that. Also, it enables us to study the full pumping cycle of the heart. Sorry. This is, you can see here something that's called fluid structure interaction. in which the valve fully opens and closes, and the blood flow patterns, the redder the colors, the higher are the velocities you see, but those are very complex blood flow patterns. Here, this is a dispersion of platelets, those blood cells that start the clotting reaction. And this enables us to study the thrombogenic potential of the device following the implantation. So I'm describing to you all these problems of this amazing minimally invasive procedure. So is there an alternative? So this is what motivated us to start developing polymeric valve technology using a state-of-the-art polymer that offers engineering flexibility and design that tissue valves don't have. And as I'm going to show to you, much favorable blood flow dynamics, biostable, hemocompatible, which means it doesn't activate the blood clotting. And this all translates to extended durability. So the idea is something that is called biomimetics, which is basically trying to look at how the natural aortic valve architecture is. And one of the things that you'll notice that it has variable thickness on the leaflets. And so we designed and optimized such a design. You cannot do that with bioprosthetic valves because what's harvested from the animal tissue is what you get, basically. And then it was used to minimize the stresses across the valve. Also, here you see the crimped valve, polymeric valve, as compared to TAVR tissue valve on the market. This is our second generation valve now that you can see right here. And we tested according to FDA standards and regulation. Here, for example, a system that is called the left heart simulator that enables us to measure the opening and closing dynamics and orifice, etc. Here you see a simulation of the same conditions. And just a small challenge of estimating this opening area exactly. So we started using machine learning approaches for that. We apply also machine learning approaches elsewhere, but I won't be discussing it here. This is how we manufacture it in a startup, which is located right here at the Long Island High Technology incubator, and we then test it, show favorable hemodynamics. In terms of the thrombogenic potential, we measure platelet activation, a special assay that we've developed. So this is a polymer valve, which is comparable and less than a surgical tissue valve, and far less thrombogenic than another TAVR device, which is tissue-based in the body. Also, hardly any calcifications are observed as compared to what we observe in tissue valves. And while this happens to transcatheter aortic valve tissue derived after 60 minutes of crimping into a stent, ours, even after 8 days of crimping, you can hardly see any such damage. All this translates to extended durability. So this is something that we test in accelerated wear testing machine, again, according to ISO standards and FDA. And our polymeric valve already crossed 1 billion cycles of opening and closing, which is equivalent to 25 years in a patient. So this is very important for the younger patients who accept TAVR devices nowadays. And this is how, by the end of the manufacturing, how the valve looks. Now, I've talked about bicuspid aortic valve patients whose situation is even more problematic. Remember, they have only 2 leaflets, a very eccentric type of orifice when it's fully open. What you see here is using a technique called 4D flow MRI or cardiac MRI. This is the blood flow patterns that are directly visualized in the patient. This is what we do in numerical simulations, and there's really good correspondence between the numerical simulations. I won't go into the details of those. Those are pretty complex. Now, our idea now, given the flexibility of design that we have with polymeric valve technology, was to start up front with asymmetric eccentric device, with asymmetric leaflets, and optimize it specifically for bicuspid aortic valve patient needs. And the optimization approach is similar to what I've described. It's also variable thickness of the leaflets to reduce flexural stresses. This enhances the durability, et cetera. But the main idea is that while it starts by being deployed in kind of a elliptical type of configuration, eventually it pushes the valve into a more circular form in which the asymmetric leaflets perform better. So this is a part of the optimization process showing how we reduce the stresses during the optimization. This is an iterative type of design optimization process. And then we wanted to study to compare how it will perform to what is done nowadays. And what is done is basically to treat bicuspid aortic valve patients. It started as an off-label use of existing TAVR devices, but those devices were actually designed for the regular tri-leaflet aortic valve configuration, not necessarily for this bicuspid configuration. So we took several patients and recreated the patient-specific anatomies and then deployed and conducted simulation of our valve as compared to, this is a very popular TAVR device, self-expandable Evolut R, and see it in different geometries. And what we compare here is the fully open orifice area. And as you can see in the various configurations of these patient-specific anatomies, our polymeric valve gets a much better fully opening of the valve. And this also translates to lower velocities during the ejection phase, which means that it will be less thrombogenic, if you recall some of what I said before, as compared to the existing devices. Now, another concern of these devices, remember I mentioned 1 billion cycles of opening and closing. Our heart is working 24/7, never stops. So it's a huge number of cycles which impose large stresses on the valve and also on the stent of the valve, and the stent may fracture. So this yet another major concern of these devices. So doing this kind of experiments in stent durability tester, you can establish something that is called the constant life diagram, with the idea that you don't want too many nodes in the stents to cross this threshold because this indicates risk of fracture. However, this type of testing takes forever. The 1 billion cycles testing that we did in accelerated wear testing machine took more than 3.5 years to complete, and it's still ongoing. Now, the question is, can we use the digital twin concept to accelerate the process? And this is exactly what we did, using the pumping living heart to deploy the valve and study it according to these curves. And this enabled us to optimize the design of the struts of the stents in order to enhance their durability. And we then compared it to other TAVR devices, these bioprosthetic TAVR devices. And see here, this is the polymeric valve. You can see that all the nodes in the stent struts do not cross this, it's called the Pelton curve diagram. Well, for both of these devices, you have many nodes that indicate the risk of fracture. So this will complete my presentation, but first of all, I want to say that all this wouldn't happen without the amazing talents of students from my research groups and doctors and in vet. And if you're around here, please stand up. So Dr. Jawad Sharif, not here, Dr. Brandon Kovarovich, okay, right here, okay, and and then PhD students, Salwa Anam, is Salwa here? Yeah, and Kyle Bayless over there, and Simon Riza, Pei-Ning Wang, Ryan Helbach, who appears here in the picture, was abducted by the industry immediately, as happens to many of my graduates. And besides that, strong collaboration with Department of Medicine, Surgery, Cardiology, and Radiology here at Stony Brook, and Dr. Slepian for Savor Heart Center in Tucson, Arizona, was a long-time collaborator and a renowned interventional cardiologist. The generous research support by the National Institute of Health and our startup company started by the support of the New York State Foundation of Science and Technology and Innovation, NY-STAR, and then industry partners. So thanks again, and I hope that you didn't suffer too much.
We have time for a couple of questions.
Jay Rose from the Poli-Sci department. A question on mitigation. Does the new device have improved mitigation for migration?
The existing devices, you mean?
No, the newer devices.
Yeah, the newer, we are only starting now, and I'd rather not discuss it too much, but some animal experiments that will be performed in Tucson, Arizona. It's dictated by the FDA. It wasn't, there's a stage that is called first in human to see how it works. I actually, by the way, part of the whole concept of a digital twin, hope that FDA eventually will accept skipping the animal experiments part and going straight from this virtual designs to building it. This is a common practice in aerospace engineering that should have been adopted in our field many years ago, still done. But all the indications and all the testing that we do in the lab and the simulations didn't go over all the details, indicate that they'll perform much better and for much longer time.
I was wondering where TAVR can end up if it migrates and how difficult it is to remove if it ends up somewhere it shouldn't be.
Now, specifically about the thrombus formation that you were asking, so if you have a better opening of the valve, the flow patterns are less complex, the velocity is lower while delivering the same cardiac output. That translates to far less thrombogenicity. Also, if the device is anchored better by improving the design of the struts of the stent, then you'll either mitigate or minimize the paravalvular leakage, which is very thrombogenic. I didn't have time to delve into that. The whole idea is that such a minimally invasive procedure won't eventually require anticoagulation medication. For example, in mechanical heart valves that have the best durability, it's mandated to give anticoagulants to the patients, and it's very complicated and problematic.
Do you mind if I ask another question? Structural value degeneration, what can happen if the tissue degenerates?
Now, polymeric valve doesn't have tissue, but when the tissue degenerates in tissue-based TAVR devices, I showed in one of the slides, the leaflets may tear up, may form all kind of noodles that will weaken it, and basically you end up with a dysfunctional valve. So this is a part of it. And part of the reason may happen because if you don't have a good expansion to a more circular orifice, then the leaflets are operating with a bit folded, maybe, and this increases the stresses on the leaflets, so it may lead to structural failure of those leaflets.
Thank you.
So I'm not as informed about a lot of this, but I wanted to ask about the research process, because you did, maybe I misheard this, but you said that some of your simulations are currently even going on right now, especially like some of them taking very long periods of time.
No, that's the experiments.
Oh, the experiments. Okay.
Now, simulations, once you do that, could take relatively short time, but you can ask members of my group what involves in very accurate reconstruction of patient anatomies, how long it takes to characterize it well, to go through something that is called numerical convergence and stuff like that. Once it works in the flow, you can do it much faster. But this is all time-consuming. Blood, sweat, and tears.
One more round of applause for Dr. Bluestein.